So today for the morning session, one of the speakers had to postpone, so we'll just have two talks in a longer coffee break. And we'll begin with Kevin, who will tell us about charge and antipodal matching across spatial infinity.
Okay, thanks. Yeah, I would like to start by apologizing if I missed a few talks, but I haven't been feeling in top shape the past few days. Fortunately, it's not COVID, I tested negative, so at least it's not that. And I would like to thank you for this wonderful workshop and to give me the opportunity to talk about some of my recent work that was done in collaboration with Federico Capone, who starts as a postdoc in Germany, and Enrico Parisini, who's a very good PhD student in Southampton. He's going to apply for postdoc, by the way, this fall. Okay, and so the topic is a very basic one, but for that reason, I think it's good to look into it with as much detail as possible. So charge and antipodal matching across spatial infinity. So what are my main motivations, at least for pursuing this? First of all, of course, the reason we're all gathered here are the developments in celestial holography and so the new perspective it gives on scattering theory. And it all started with this amazing observation by Andy and collaborators, Temple in particular, that BMS charge conservation is equivalent to Weinberg's graviton theorem. And the standard assumption that goes into this equivalence is the antipodal matching conditions on various gravitational fields, so the boundary mass aspect, angular momentum aspect, and the shear. And in particular, once you assume this, it's pretty obvious that it implies BMS charge conservation across spatial infinity. So that's one important motivation. Second important motivation for me is to understand what are the degrees of freedom in gravity that we should be looking at, that we should be considering. And of course, to answer this question, I have to specify a set of interesting physical situations and events I would like to describe. And so there are various technical questions that go with this. So if we think of, for example, the boundary expansion, should we also consider terms that are logarithmic in R? What are the proper fall-offs as we go to square plus minus, so towards spatial infinity? That kind of question. So I think a good understanding of the asymptotic degrees of freedom in gravity and the way asymptotic symmetries structure them can already buy us quite a bit. And as an illustration and advertisement for another work, so recent improved understanding of the phase space and BMS fluxes yields loop corrections to the subleading subgraviton theorem on the nose. So that has been discussed. I guess there is discussed in these papers, but that would be the topic of a different talk. Right. So feel free to ask any questions anytime. Right. So what is the roadmap of this talk? The main message I would like to get across is that antipodal matching can be viewed as a property of a solution space that satisfies specific fall-offs near a square plus minus, so near spatial infinity. And it's not, so you don't need to give the antipodal matching a priori on data both at square plus and square minus. It's enough to specify the U behavior at square plus minus. And that's more satisfactory, I think, for example, from a perspective of the evolution problem, where you would just like to give some set of initial data, evolve it, and then see that there is antipodal matching. So the strategy is the following. We start by prescribing certain fall-offs in U at scri plus minus. In fact, such that the BMS charges are finite in that limit. And then we're going to map the data close to scri plus minus to data in the future of spatial infinity. So here, the notion of spatial infinity I have in mind is a blow up of I naught in terms of a three-dimensional hyperboloid, so three-dimensional de Sitter space. And yes, so that's the future of this hyperboloid that I'm thinking of. Then we're going to use the evolution equations coming from Einstein's equations to evolve backward in time this data to the past of this hyperboloid. We're going to use the map again to go to scri minus plus this time. And then we're just going to assess whether there is antipodal matching. So that's the strategy. So this is, it's not the first time that this has been discussed in the literature. There has been a paper by Cédric Troussard and two papers by Prabhu and Shehzad. There are a few novelties with respect to those earlier work. So we have a systematic way of mapping data between scri and I naught. And perhaps most importantly, from a technical perspective, we have a full treatment of the nonlinearities that are important in deriving the antipodal matching of the angular momentum aspect. And we also discuss explicitly the matching of BMS charges from scri to the truly conserved charges at spatial infinity. Okay, so this is a picture that can help describe the setup geometrically. So this is well, the Penrose diagram of Minkowski space. Outside the light cone, we can foliate Minkowski space with three-dimensional hyperboloids with constant curvature, so namely DS3. And we're going to be interested in the hyperboloid that is closest to I naught. Now, something that is not captured in this picture is that this last, I mean, in an asymptotic sense, this last slice does not attach to the middle of scri, but actually attaches to the ends of scri plus and scri minus. Yeah, that's right. Yes, indeed. But that's the limit I'm going to be interested in. Yes, so right, and the goal will be to look at data at scri plus minus here, and then map this data to the future of the last hyperbolic slice, evolve the data backward in time, and go to scri minus. Yes. A non-singular, I mean, so you'll see in practice what's going to happen. So what I mean, I naught is not as such so useful because it's only a point and fields are not single valued there. So yeah. Maybe on like on that diagram. If you sneeze, yeah, you put a perturbation or yeah. Yeah, I'm not right. That's right. So yeah, it doesn't rely on this at all. So it will actually all be coordinate based, and you know, short shield is part of the solution space that is considered. So yeah. Yes, Andy. I mean, I think you realize on some
light ray travels on drive block. And that one's a very difficult hard solution that don't put that into the matching. But another way to think about it, I mean, yes, it is an assumption, I suppose, but it's an assumption which you didn't find about it. So,
yeah.
So every solution that is built up in particular on plastic arguments will say that imperial matching conditions. So the ones that don't, I mean, you could always put some particularity and let it look at the way that, but everything doesn't obey it. And it shouldn't be water.
Yeah.
Black holes certainly bad. Black holes certainly bad.
Yeah.
They're not smooth. I don't. It's not a. It's not smooth. One way of thinking of it is you can form a compact pi and you put a zero on the back of the cylinder. The field is continuous so long as you have to go through. And that's conveyed by. I don't think. I think it would be very hard to present anywhere in the literature. The solution. Any solution that fits in phase is funded.
Yeah. So I guess here I want to give a different perspective on this, which is more about this property arising from some specific type of data that you put here. Yeah. Right. Yeah. All right. So yeah. So I'll just start by describing how to map data from scribe to I0. Then I'll discuss the antipodal matching relations that come out of this, and then I quickly talk about matching of charges, BMS charges at scribe to truly conserved charges at spatial infinity. And then I'll give some perspective. All right, so we want to map data from scribe to spatial infinity. So first I need to describe data at scribe, and we're going to use our favorite boundary gauge. So if I impose Einstein's equations, this and impose that asymptotically it's basically Minkowski, then this is the form of a general solution. So there are three quantities that I'm going to be looking at: the Bondi mass aspect, the angular momentum aspect, and the shear tensor. And they're all functions of the retarded time u and the coordinates on the celestial sphere xa. And in addition, there are two constraints equations that constrain the u behavior of m and na. I will describe them in a bit. So yeah, so I'm interested in looking at the data close to scribe plus minus. And what I'm going to do is very naive. I'm just going to say, let's assume that there is a Taylor expansion in 1 over u, close to u equal minus infinity. And that the leading behavior is just a constant. So of course, this can be refined later on, but this is what I'm going to work with. And then I have to plug this in the evolution slash constraint equations for the evolution of m and na. And if I assume that in this limit, the matter stress tensor does not contribute, which is reasonable since we're close to spatial infinity, what I find is first, or this very familiar formula that C naught AB is characterized in terms of one single function, which we identify as the super-translation Goldstone mode. And then another thing that happens is that M1 and C1 have to be 0. And this is all I'm going to need for the purpose of this work. Right, and in fact, this is precisely, I mean, at least the fall-off in the fact that there is no 1/u term in C. So says that there is no 1/u squared term in the news, which is the derivative of C. And this is precisely what has been used in order to derive the subleadings of graviton theorem. So that's not so surprising that this happened. Right. So that was null infinity. So now let me go to the neighborhood of spatial infinity. And for this, I'm going to use the so-called Bike-Schmidt gauge, which is basically a coordinate version of the Ashtekar-Hansen formalism, where they introduce also some three-dimensional hyperboloid that parameterizes the directions of approach to I0. But it's basically the same thing. The equations are actually the same when you look at them. So this is just radial ADM decomposition. So rho is the radial coordinate, and as rho goes to infinity, we approach spatial infinity. This is the lapse, this is the shift, and this is the induced metric on a rho equal constant surface. And again, we can do some asymptotic expansion of these functions. And there's going to be three quantities I'm going to look at. There is this sigma sitting in the lapse. There is this KAB. So those are the two leading dynamical fields. There are three-dimensional tensors on the Cetor space. And as a comment, they play the role of potentials for the leading electric and magnetic biotensor at spatial infinity. And then there is also this guy, JAB, which is subleading. So in that gauge, we need to impose some boundary conditions in order to have a well-posed action principle. And what we need to do is to, well, impose, oh, sorry, I forgot this. There is this quantity here, HAB. And this condition precisely tells you that it has to be the metric on the unit, the Cetor 3 hyperbole. And we also have to impose that the trace of K is 0. And that gives you a well-posed action principle. And now we can look at Einstein's equations, and they imply those evolution equations for the various quantities. So these are just second-order differential hyperbolic equations. They look like, so for the leading fields, they look like free field equations. For the subleading field, JAB, it's a free field, but it's sourced quadratically by the leading field. And this is where the story gets a bit complicated with respect to JAB, but okay, it's gonna work out. And again, the trace and divergence of this quantity are also constrained in terms of this leading data. So yes, so we have the equations of motion near spatial infinity. And what I would like to do is to characterize the free data in this in this dynamical system. And for that, first I'm gonna use some specific time coordinate system on the hyperboloid. So this is the global time on the Cetor space, and this is just the round sphere metric. And I'm interested in the limit tau goes to infinity, which is the future of this hyperbolic. And then we can do something that we are very familiar with from ADS-CFT. We can do some sort of Pfefferman-Graham type expansion of the various dynamical field and identify where is the free data. So for sigma, for example, the free data is here. There is this sigma -1, it's a function on the sphere, and there is this sigma 3, which is also a function on the sphere. And for various components of K and J, well, the free data would be in fact, right here, except that there are some constraints between the data because there are trace and divergence constraints. But this is where the free data would be. So now I have a characterization of the free data in the future of the hyperboloid. I have a characterization of the free data in the past of Scry. I want to map this data onto one another. Right. So for that, I'm just going to use coordinate transformations. And at 0th order, this is just describing Minkowski space in two different coordinate systems. So UR are the boundary coordinates, rho tau are the Dijk-Schmidt coordinates. And I have to make sure that I work in a regime which is compatible with what I'm doing. So what I want to do at the end of the day is work in the regime where R goes to infinity, U goes to minus infinity. But R is bigger because I first do the large R expansion and then the U expansion. In Dijk-Schmidt, I want to first do the rho expansion and then the tau expansion. And then I can see if this makes sense at all. So I can take the ratio of U and R and see that it's very small if I take tau to infinity. So this seems okay. So and in fact, so it works out perfectly well. All right, so this is the 0th order transformation. I just need to extend it to including like perturbations about Minkowski space. So I just need to generalize these transformations, including corrections. So this is pretty lengthy. It's in the appendix of our paper. I'm not going to talk about that. It's not very interesting. But what comes out of the process is a map between the various data I was talking about. First interesting fact is that the leading allowed data, so the data associated with the leading allowed asymptotic behavior at large tau, turns out to be 0. So in a sense, the boundary phase space that I started with only maps onto sort of half the allowed phase space, or the phase space at spatial infinity, and this will play, a crucial role. And then for the subleading data, we have an explicit map. So the boundary mass aspect is basically sigma 3. The shear is in this component of KB, and then the angular momentum aspect is in this guy, sits in this guy. Since we have all the free data, all the one we wanted to look at, the free data at spatial infinity, we can actually reconstruct the full solution on the hyperboloid, and we found some interesting thing is that this field KAB is of a very special form. It can be described in terms of a single potential phi, and this precisely yields vanishing of the leading magnetic Weil tensor at spatial infinity. And this has been used like extensively in the literature as an assumption, first by Ashtekar and collaborators in coming up with a good definition of Lorentz charges at spatial infinity, but also in more recent work. So Jakob and I, we use this in deriving the effective action for super translation modes. It has been used as an assumption in earlier discussion of charge matching. And we see that, it's a generic feature of the solution space we're looking at. Right. So, okay, so we have the map between data that we're interested in. And now we want to assess the antipodal matching relations using this map. And what we would like to show is basically this. So here, I think you all know what this means, but basically the value of m at a point x at square plus minus is the value of m at square minus plus, but on the other side of the sphere, and similarly for the other fields. And the claim is that these antipodal relations follow from parity properties of those fields, sigma kb and jb, under time parity reversal on the hyperboloid. This is, I mean, this is intuitively clear that this would yield something like this. So what we have to do is to show that this is indeed true. And I'm going to work out one example for you, which is that of the mass aspect, sigma. So this is the equation of motion on the hyperboloid. We want to look at the solutions, so we do a harmonic decomposition in terms of spherical harmonics. And the coefficients can depend on time. So S is tangent tau. And these coefficients turn out to satisfy this Legendre differential equation, which has two types of solutions, the P's and the Q's. And the P's and the Q's, they are Legendre polynomials. They have different properties. So they are associated with different asymptotic behavior, and they have different parity properties under S to minus S. S goes to minus S. But an important point we found is that starting from the boundary data we're interested in at null infinity, we find a restricted asymptotic behavior in tau, because the leading data, which was called sigma -1, was just 0. And this was associated to order exponential tau behavior, but we found that this has to be 0. So the order exponential -3 tau is the asymptotic behavior of the solution space we're interested in. Now we can just look at what is the general solution with that asymptotics, and it only involves the P's. And now we can just use the parity properties of the spherical harmonics and the time reversal properties of the P's to show, to directly show that sigma is even under time parity reversal. This was already known, already discussed in '92 by Herbertson and Ludvigsen, and more recently by Troussard. So this is not new, but what we've basically done is to extend this analysis for the shear and the angular momentum aspect. For that, we needed this map that we worked out. And just to give a flavor of the technical complication that arises. So what I just described was this equation. It's just a homogeneous equation, very simple. Here it's not too bad either. It's also tractable. Here it gets much more complicated because you have this source on the right-hand side. So you have both source-free solutions and source solutions, and you have to see whether the source solution is not contaminating the parity property of the sourceless one. But thanks to the fact that a lot of the free data in sigma and k is actually absent, the source solutions are sort of subleading with respect to the homogeneous solution. So the homogeneous solutions still tell you the answer. Right. So yeah, so the right, just yeah. So as a summary, this holds, and we're happy. Okay, so now I can just briefly discuss the matching of BMS charges from scry to spatial infinity. So there are various proposals for BMS charges at spatial infinity, at null infinity. They take this generic form, and the various proposals are parameterized by these two coefficients, alpha and beta. Fortunately, we find that in the limit where u goes to minus infinity with the follow-ups we've assumed, all these proposals, they just collapse to the same expression. So that's good. And in fact, it's quite non-trivial why this term drops out. It's because of this identity on the sphere, and that follows from the fact that YA is a conformal killing vector, and C0 is a pure super translation. So it only depends on the super translation goals or no. And now we can just see whether this quantity is equal using the map we've developed to the truly conserved charges at spatial infinity that have been constructed by Compère and de Hoek already quite some time ago. But the funny thing about this story is that at this time, it wasn't clear what was the relation between the symmetry group at spatial infinity and the symmetry group and the BMS group. But this has been clarified in recent years. These ones? They were conserved in the sense of being constant along a cut of this hyperboloid. Right. Yes, but one would expect that, you know, as you go from to scry plus minus with your BMS charge, you reach the future end of this hyperboloid, and then you can just evolve backward in time along the hyperboloid, this conserved charge, if they match, of course, which is what we basically show. So you can you take your charge, you go to scry plus minus, you jump onto the future end of this hyperboloid, and then you use these conserved charges along it, and then you jump on the other on scry minus, and it all works out. So this is basically what we describe in this part of the work. So this is a true conservation law, really, in the usual sense. And the BMS charges that at null infinity, yeah. No, not along scry plus. I agree, but usually, I mean, like conservation laws. In the standard way they describe at spatial infinity, right? So you look at your ADM mass, for example, and you want to know whether the ADM mass is conserved as you go upward in time. But then, of course, it's not when you jump to null infinity, you don't expect true conservation because now the null infinity is an open boundary, which is not the case for the boundary at spatial infinity. There's no flux through I0, so there you can really expect a true conservation law. But once you jump at scry, of course, there is leaking of energy, so you don't expect a true conservation law. No, it is, but I would say not along scry. Yeah. 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 Let me discuss this a little bit more. So let's first zoom out here. So we have this hyperboloid. Sorry, what? Ah,
big one is on you.
the blue. Yeah, that seems better. There is this DS3 hyperbolic, and here we can take a cut, which is the S2, and define a charge over here, which will depend on time, let's say tau, because there is this time parameter tau, which is a BMS charge. So there is a t parameter, there is a YA parameter. And then what I'm saying is that it's conserved in the usual sense that d tau q tau is 0. So this is the conservation law at spatial infinity. And in particular, there is ADM mass in here. So this is the usual type of conservation law you would think of when you learn classical mechanics, I guess. Now, of course, there is a different thing you can do is to look at a cut of scry, which is also an S2, and define a Q tilde, let's say, which will depend on U, on the retarded time position. Also a BMS charge, so T by A. But of course, here we know that it's not true that du q tilde U is 0. As exemplified by the Bondi massless formula, for example. Yes. Why? There is a simple explanation for that. It's just that here in defining the dynamics of GR, we made sure that there is no flux, let's say, of energy, but technically we would say symplectic flux going through I0. So this is absent. However, there is flux going through scry, a flux of energy in particular. You have gravitational radiation leaking out of scry. And this is the cause of, let's say, the Bondi mass loss formula. Say again? No. All spatial, all like space-like hypersurfaces end up at I0. Right. No, I mean, if you think of space-like hypersurfaces, they all go to I0. Yes. But they all go in a sense, they go like this, like this. Yeah. Sure. So this is basically what, but this picture is a little bit confusing with respect to that. So it's better to just blow up I0 and see that the slides go up that direction. Why is the charge along the boundary? This generically happens in gravity and gauge theory. Yeah, it's sort of there are lower dimensional charges. So anyway, so here we have those two different types of charges. And what we explicitly discuss is the fact that if you take the limit u to minus infinity of those q tilde, it's exactly equal to q tau. So you can like glue those charges onto each other. So are we clear now on the? Yeah. No, because there was no explicit map. Yeah, I mean, in this work I mentioned before, they by Prabhu and Shehzad, they already discussed this, but with a little bit less of generality, and also not as. I mean, here what I like about it is that it's very explicit. We have two coordinate systems. We map data onto each other, and we can just look at these expressions and see that they're equal. Right. Yes. How? You count because there is no flux at spatial. I mean, near is really at scry. Is really once you jump onto scry. Yes. Yes. Yeah. Because this this Bayek-Schmidt setup does not capture scry. It barely, joins it at tau goes to plus infinity, but it does not like allow us to capture any finite portion of scry. Yes.
Maybe I missed something, but so d tau of q is 0, so you can evolve it. But du of q is not.
Right.
So you evolve it backwards to
no, they're equal. They're equal. I mean, you just have to look at this expression. So there is this expression. This expression here. And then we know what is the conserved charge on the hyperboloid. And we have the map between. So we can, for example, what we do in practice is we express the charge at I naught in terms of late time data. And then we have the map between this data and those quantities. So I can flash it again. It's basically here. So this is late time data on the hyperboloid. And this is M naught, and there should be a naught here, and A naught that precisely appear in this formula here.
Another way of thinking about it is simply convert one from the regular, you take the market and the limit for the equation infinity. Simply still convert in the limit, the end of the hyperboloid.
Yeah, I think that's what I was describing. But just to be sure, there was no confusion. The charge is q tau here. They're only defined on this last hyperboloid, already at as rho goes to infinity. But then you're right that so basically this two sphere here is the celestial two sphere at scry plus minus. Okay, so I think that's pretty much it. So let me just give some perspectives. So here we've made some assumptions about the type of U expansion we have. Andy.
But you want to just be near spatial. You want to consider hyperboloid. Does it have to take up a lot of the space? How do we stretch it out?
Yeah. So this, I guess, it's the comment I was making that this last hyperboloid does not attach to the middle of scry as we would like conclude from looking at this picture. It really attaches to scry plus minus and scry minus plus, and this you can see by looking at this. So you just want to take. Yeah, I mean, if you right. I mean, this is you know, this is an optical artifact that the last hyperboloid would just be a point, because as you know, Penrose compactifications, they don't preserve length. So it you know, it becomes sort of singular overlay. Yes. But just a comment about what you said. So for light rays, I guess this is true that a light would go from the North Pole to the South Pole. But when you look at massless field equations, this is not really true anymore, because you can, in fact, you can have in general solutions that are both that are either even under time parity reversal or odd under time parity reversal, or just a general superposition of that. But what we show here is that there is really only one type of solution that matters for us, and they have definite parity, time parity property.
So your hyperbolic one is down there at zero, will not be it will be like a spectrum. I don't even understand why they'll be
Yes. It's still the Sitter space. Yeah, bigger. No, but okay. But okay, but this. No, but wait. Okay, I think there are two different things here. I think there are two different things to be discussed here. First is that let's forget about where the Sitter space comes from. But so Andy, your point was that if you take a light ray here, it propagates and it goes to the other side, right? Yeah. But even though I would agree for light rays, if I just consider some free field equation, which is not massless, maybe that's the point. It's not massless on the hyperboloid. So this is a massive. Oh, wow. Sigma equals 0. It's actually a massive equation on the hyperboloid that describes the propagation of the Bondi mass aspect from scry minus to scry plus. So you cannot actually use that argument.
Okay, but it's still like
massive.
Massive field still on the light
they have a signal on the light cone, but
So if we started shortening that, that would be it seems like to get it small on both sides, you can shorten it. And then I don't see how close that would be allowed, but the propagation of this
okay, let me get to that in a second. But yeah, but here already, I mean, the argument with light rays, I'm not sure it's that good in the sense that it's the massive equation that describes the right. Yeah, but if you have if you have some full data here, you okay. No, yeah, I agree. It's the inside of the light cone.
So now if we start shortening that, we bunch it down to the two, the I0, I don't understand how it gets as well.
Okay, so let me try to clear up that. It's still full, but it's just that the picture is a bit misleading, I think. I think the picture is misleading, that you think that this is a point, and of course in Penrose conformal compactification, I0 is a point, but this is not what we're really doing. We want to still keep track, let's say, of the directions of approach to I0. There's definitely more structure to spatial infinity than just being a point, or at least you can choose in which direction you're approaching it. And for that, you need a hyperbole to describe it. But said more simply, let's just forget about the conformal compactification and just slice the Sitter space. Sorry, let's just slice Minkowski space with the Sitter hyperboloid. So this is the transformation. Let's see. So the point I wanted to make, maybe it will help, is that if you consider any row finite and take the limit tau to infinity, so the future of any of these hyperbola, you end up at u equal 0. So which indeed is what is depicted here. You end up in the middle of scribe. But this is not the regime we're interested in. We first want to take rho to infinity, and then exponential tau to infinity. In that case, you really go to u equal minus infinity. It's an order of limit. I don't know if that helps. It's usually a big confusion. Yeah. Yeah, I mean, here is because I start. So here, I really only describe the matching between scribe, the overlap region between scribe plus and a neighborhood of I0, because I use retarded bounding gauge, which are not really appropriate to describe that part of space. But I can do the same game with the other boundary coordinate system. Yeah. Yes, Sabrina. Mm-hmm. Right. Yes. Yeah, that's it. Yeah. So yeah, with this we have like we have a full description of this thing. There's no scribe. I mean, we have one coordinate system for this. We have one coordinate system for the neighborhood of this, and we know how to glue these things at their edges. Yeah. Okay. I mean, you can go in space-like directions, not only at a fixed time. You have a three-dimensional. Yeah. I mean, maybe what you're saying is that this bit this collapses onto each other somehow. I mean, there is still like something in the middle. It may be small in that picture, but there still is. Yeah. Yeah, exactly. Yeah, definitely.
No, but we get the causal structure right. And Penrose diagram has this property that is as we look at slices of larger quantities, relative to kind of large tone of the future value instead of but there's only things and find out they really can be that five. Where to reach the you have to think out of where is the magic idea of the
No, there's not really any I0 in this picture because I don't do any conformal compactification. Yes. Well, by the way, maybe I don't know if that helps at all, but this is just a coordinate version of the Ashtekar-Hansen formalism. So, yeah. Okay. But okay, so yeah, maybe let me just end with this perspective. So we've assumed some expansion in U close to scribe plus minus, and of course you might question that. And something that could be interesting is to understand the maybe 1/u tail effects that would be in correspondence with logarithmic terms in soft expansions of amplitudes, and that has been discussed by Ashok Sen. Here we really only looked at the phase space, not including superrotations, and the reason is that it hasn't been incorporated into this Bayek-Schmidt framework yet, but this is work in progress with Federico and Enrico. One can ask about logarithms in R in bonding gauge. So one can try to further enrich the phase space we're looking at in order to accommodate more physical events of interest. But okay, this is the the situation so far. We have a systematic way of mapping data from scribe plus minus to the future of this hyperboloid, and one can do it to arbitrary order in the expansion. And then there is this thing that I haven't touched upon at all, is this sub-subleading antipodal matching condition, which has been argued by Fredel, Franzetti, and Raclario to yield the subleading soft graviton theorem. So that's something that could be done as well. So yeah, that's all I wanted to say. Thank you.
Actually, I have one.
Yeah.
Is there any obstructions for your analysis to implement in higher dimensions?
No, I think you could do it in principle. To be honest, I mean, most of the work, I think essentially all the work about this framework for spatial infinity has been carried out in 4 dimensions. So you would need to sort of start from scratch. But in principle, you could do it.
Yeah, I was just wondering, like, it probably would be the same U fall-offs, right? Since the higher dimensions, it would be higher dimensions in space. And so.
You mean whether we can expect the fall-offs to be the same in U?
Yeah.
I haven't thought too much about it, but I would think so. I mean, at least if you just think about having finite BMS charges in that limit, then you would go with the same thing, I think. Mm-hmm. Log U in the shear or in the shear? Log U, like overleading. Yeah. Yeah. I mean, it would be a drastic modification of everything we've worked with so far. Yeah. 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 Well, I don't think there's a really big, because the other news, the Gerach, I mean the thing with the Gerach, it just eats up a U term, which so in the it eats up a linear piece in U. Yeah. 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 Yeah, I don't have a good answer to that. It's
yeah, so I guess the self-leading graviton is just the first in an infinite. I mean, the leading graviton is the first in an infinite power. And I guess we now know certainly to the level that those all fit together into a W1 plus infinity.
Yeah.
And the W1 plus infinity, I guess, was first understood, but in a very different language by Penrose. And I don't think Penrose understood anything about the relation between it was a solution generating thing. I don't think he understood the relation between super translations and the rotation, so on, or maybe he did, but but that W1 plus infinity exactly acted on, it was a transformation on the celestial sphere. So somehow we should be able to see it there. And it should come out to be possible to see the whole power of symmetry being preserved rather than one at a time.
Right. So is that does it, according to Penrose, does it act as a area preserving homomorphism? Something like that.
Area preserving.
Yeah. Well, so I'm not familiar with that. Is it? What's the reference?
And I guess it's recently been made very explicit in the sense that the W1 plus soft graviton to generate the W1 plus infinity by the same as the linearization of which is generated by the W1 transformation by some people who feel that others will do it on that on that paper. So there is something pretty explicit in the sense of actually understanding what the metric is involved in that, which is bringing it much closer to the language that you're using. So I think that the linear isometric perturbations that are produced in this way are growing in it. All right. Maybe growing in one direction. Same way that a plane would as one was generated.
Okay, so
They both right. They may grow in one direction, but that's not incompatible with things that people are saying. That these two sort of competing stories, and there's more. And that's so there's all these different formulas which are asking the same question, right? There's final diagrams, there's the formula sum, there's the other side of the formula sum, and they all they all end up on the same group. Clearly, they're all the same thing, but the detail correspondence is difficult. But even in the asymptotic story, there's the work by Lana and others in which the asymptotic symmetry start off as big transformations, which are rather than being subleading.
Yeah, they're
growing,
yeah.
but then you do a subtraction.
Yeah.
So probably the Twister presentation of the graviton wave function is going to land on something more like what in the end is Campbell a lot of it. I really think papers with other people some time ago, in which we did understand which sounds much closer to the kind of thing you're doing. We understood the asymptotic in terms of if you take some boundary conditions on a spline, and then you want to evolve into the pulse, you might have thought that if you specify the sensor, that would give you a unique evolution of the pulse. But it's not quite true because of pure power series expansion. To get an integration, you look at the Penrose equation, you get an integration constant, which doesn't depend on you and everything.
Right.
And that integration constant is like a goldstone. It's like a goldstone boson. That would be the thing that would naturally appear in your setup.
Yeah, so perhaps there's
how it all has the same thing.
So I don't know. It sounds like perhaps one needs to extend a little bit the phase space that one is working with here in order to start seeing those symmetries. I mean, if you're talking about overleading.
We did a subleading.
Yeah, right. Yeah, right. Yes, yeah, right.
Because you take the overleading thing, you subtract from it, and the version constant leading thing is the difference.
Yeah. You're saying already in the standard Newman-Penrose thing, there are all those integration constants.
Yeah, in Newman-Penrose things, there are integration constants at every order.
Right.
And in one of their papers, they have infinitely many conserved quantities. Each of these they thought was a conserved quantity. Oh, so they add interactions, and when they add interactions, this is basically conserved quantity. But those 10 new conserved quantities are there because they have the wrong boundary conditions described. They essentially include boundary conditions which fit over the other. And by conserved, I mean, they said it was exactly conserved, not right. What? Sorry, I can't hear you, Andre. Well, I don't think you want them. I think those the Penrose number boundary divisions are wrong. Those are the ones that you could drive the ceiling there. Their boundary conditions have to do with the way that the components of the valve sensor fall off as you go back to dry minus, and they impose them in order to, I think, have some kind of smoothness at I0, and the smoothness at I0 sets a lot of BMS charges to 0. It's extremely unphysical thing to do. Those 10 conserved charges are not conserved. If there really were 10 conserved charges of general relativity, ignoring vacuum degeneracy, not 4, we keep learning about it in all the textbooks. It was a thing that the same relativity was never retracted, but not physically correct. They had 5 in the so it was illustrative of the trouble you can get in if you use the wrong boundary condition I0. You don't use the integral matching. They didn't know about the integral matching. Sorry, can you speak a little louder on there? I thought that 10 or 5.
Your words are
Yeah.
muted exactly what you want to hear.
Those 10 conserved charges, when they say 10 conserved charges, they mean conserved the constant along the line. There are no second charges. They don't, you can't, there's no flux of them. That's what they thought. But that was definitely wrong.
No, I couldn't.
She's saying that the Godesgar brothers they have derived them as a subset of subleading charges so you take like BMS charges and you expand them in 1/r, and you keep track of the subleading terms.
Yeah.
They find that those 10 charges they live somewhere in those subleading terms, right?
Exactly.
Yeah.
Thanks.
Well, I don't know about that, but the Newman-Penrose paper had a charge which was independent of flux. That's wrong.
Yeah, I don't think in their paper they say that it would be conserved.
And Christian Uller talked about this and explained what that was. So, but it was also a problem when they didn't know about the mix at all. Andre, you're talking about charges that are conserved in the sense that numbers on scribe minus equal numbers on scribe plus. Even super translation charges are not constant in use. But anyway, I think that W infinity could possibly be an organizing.
Sure. Yeah. I would love to hear more about this. So maybe I can talk to you later.
Well, it's complicated.
Yeah.
I don't know how to do it.
Yeah, or even some references to start with.
I think the last paper trying to break it.
There's a lot there.
Okay, but he's breaking things. We trying to get them.
Yeah.
Right.
I'm not answering anything.
Yeah.
Okay, well, maybe we should move on to Piotr's talk.